The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, my name is Renata. I'm the moderator of today's webinar dedicated to discuss the best practices in systems modeling. We chose MBSE. What's next? Welcome and enjoy. This session will introduce you to the main MBSE pitfalls and explain how to avoid them using MagicGrid, a modeling framework for complex systems. The session will be hosted by Aurelijus Markevičius, MagicGrid Senior Solution Architect for Model-Based Systems Engineering, mostly based on SysML and UML, and Defense Architectures DODAF, MODAF, and NAV. He runs training and consulting sessions for the world-leading companies all over the planet. Aurelijus is also a co-chairman and one of the leading architects for the current OMG UPDN UFA Standard Development Group. The presentation will take approximately 50 minutes and the question-answer session about 10. You don't have to wait till the end to ask questions. If you have any, just type them in the chat window, and Aurelijus will answer some of them live after the presentation. And due to the limited time, the remaining ones will be answered later and published with the link to the video of the recorded webinar. So Aurelijus, are you ready to start?
Yes, thank you, Renata. Hello, everyone. So today our topic is we chose MBSE. What's next? So the objectives and aims for this webinar is to introduce MBSE pitfalls and explain how to avoid them, to introduce you to the MagicGrid, to our new unified modeling framework for complex system design, explain major SysML concepts and diagrams, show how to trace model elements in different views and among different projects, share worldwide experience building system models, show a consistent modeling case study, and explain how to use modeling tool features efficiently. So let's start from the definition of modeling solution. So in general, we say that the modeling solution is the combination of three major components, a combination of language, methodology, and tool. And they all together provide productive infrastructure for applying model-driven development in the context of particular organizations. Basically, all three are very important. When we talk about language, we talk about SysML. And the SysML, for those who do not know, is the systems modeling language, which is a graphical modeling language for specification, analysis, design, verification, and validation of systems. The language is developed by Object Management Group, and it is dedicated to model complex systems. And there are multiple tools supporting modeling tools, so today we will see some examples. See some examples from a Cameo Systems Modeler tool. Okay. And SysML language is considered to be the enabler for model-based systems engineering, and the major structure that is presented in some books of the language is as follows. So it consists of structure, behavior, requirements, and parametrics. So these are four main components for the language. However, it is very important to understand, and what is stated by CoE, that the modeling language is just a language, and it must be combined with methodology to be useful. So you have to have some kind of method, and it is very similar as taking natural language and talking about the dictionary, where you can find words, but to be able to build meaningful sentences. So you have to know more how to do this. You have to follow some kind of process. If you don't do that, we have some examples what happens in modeling practice. And this example shows the activity diagram that is composed of 450 actions, 950 control flows, and there are some other facts about the project, that it was used for model-driven development. The code was generated out of this model. 50 engineers worked for 4 years, so basically for one guy it's 200 years work effort, and more than 2,000 diagrams like this was created. So actually this project, as you probably can see, it failed, and it failed when the main architect, the main engineer left the company, because it was impossible to maintain this kind of diagrams. So this is just one of example what can happen in modeling practices. Now let's go through some of the common MBSE pitfalls that I can see throughout different companies. For example, the first one is unmanaged abstractions, and this is more about raising level of abstraction and creating system in defining it in several levels of abstraction to reduce complexity and to be able to present different viewpoints for different stakeholders based on their needs. Right? Not everyone is interested to see a very technical model. Some of the stakeholders, they want to see more high-level models like use cases, activities that are not very technical. So when you have unmanaged abstractions, it brings ambiguous understanding. Sometimes you duplicate information that you could avoid. And of course, sometimes it brings dependence on technical platforms. So this is especially when we talk about very detailed models, about mechanical engineering models, about software code that we generate. So we have to make sure that the model is not one-to-one to programming code. This is not what SysML is used for. And so there are some recipes for this. So one of them is raise level of abstraction. So we are going to discuss the framework that we propose and the abstraction levels that there are in the framework. Just very simple example taken from one of our customers is that, for example, they're using framework of where they have functions. They define functional architecture, then they define logical system structure, and finally they define physical systems where they perform different trade-offs. So this is just one of examples of how you can arrange SysML model. And during the presentation, we are going to discuss it a little bit more details. Now let's go through the rest of the MBSE pitfalls, which is disintegrated model. So this is the second one, what I can see all the time. And this is talking about different teams working on the projects that are not related. So it means that projects simply lack traceability. There are no relationships between the two. The good example sometimes is where we build concept in one model, and when different solution teams, they are providing models for different subsystems, and they are not linked. There are no traces between this model and the model at the concept level. So it's difficult to maintain when we have separated models, or even some information is in the documents. It is very difficult to maintain when there is no single source of truth. Then we of course have duplicated and redundant information in different places. And the simple answer to the problem is to make a model the single source of data. So to make sure that all different parts of the model, no matter their SysML model or software model made in UML, they have to be connected. The other MBSE pitfall is too complex diagrams. This is a very common mistake. I already explained a little bit what happens if you have very complex diagrams with hundreds or thousands of elements in them. So it brings ambiguous understanding. It's very difficult to communicate. You have to understand that modeling is basically for communication among different teams, among different people in the team, and you have to make sure that you're actually using language the way that people can understand what is the subject for communication. And also it hides incompleteness issues. When you have amazingly large diagrams, you usually do not focus on the particular aspect and miss some of the issues that are here on the diagram. And it's also very important to understand that model is not equal diagram, and the view is not equal diagram as well. So when we model, we're actually creating a model, adding concepts to our database, and finally we can reuse these concepts to build multiple different diagrams. And when we talk about view, we have to have in mind that it's not only diagram that can be useful. You can build matrices, tables, charts, and various different kind of representations of the model. So this is exactly The resolution is to use different views to represent model data, and view is definitely more than a diagram. For example, view can be table, can be matrix, it can be chart, dependent on what kind of methodology you use, right? Different kind of time charts, graphs, dynamic graphs, and so on. And the final MBSE pitfall, before we go into the approach, is that different roles are not involved. And this commonly happens when we talk about systems engineers, about mechanical engineers, about electrical engineers, about project managers, about software engineers working on the same project. This is very related to having separate models and in a different media or different tools, and there is no way for these guys to communicate. So this brings gap between cross-functional teams, and of course sometimes the model becomes single aspect oriented. So when others do not have ability to comment or review models made by, for example, mechanical engineers team, so they definitely are very oriented to the domain that people are working in. And the resolution here is bring the different roles together, and having some kind of framework could be an answer for this, right? Because we are talking about system engineers, project managers, software engineers, requirement engineers, and other roles. So actually, to be able to deal with all these issues and to start working with some framework or defined method, first of all, we have to understand the concept of modeling culture. And we define it as a combination of three main components, which you can see in the slide: modeling, model usage, and model governance. So these three are the most important. Today our focus is on the modeling, so this is how we are creating model. Then of course it's very important to talk later how you use model, how you share model among different users or stakeholders, and of course finally how you manage the model. So there will be a bit of all of these three components, but basically, as I mentioned, we're going to focus on modeling. And once we talk about modeling culture, it's also very important that in your organization you have people who knows modeling, who are advanced, and who can always help. So we call these guys center of excellence. And of course, the number of principles that you have to go through. So first of all, these are main ideas of how to start once you decide to go to MBSE. So first, you need to establish center of excellence to bring experienced people together. Then to establish modeling guidelines to make sure that you all speak the same language. Have to have reference model for this, so this would work as an example, so everyone knows how to create a particular diagram or particular view. It's easier to introduce new people in the team and so on. Of course, with the example, it's always good to have textual documentation, and of course it is good to tailor tool, including some automated model validation rules that helps you to make sure that you are following the best practices and following the method that you are using in your organization. Then, of course, every model must have an owner, so you have to make sure that models are consistent, that in terms of form and in terms of content, of course. Then you have to decide on configuration management of how you govern the models, permissions, branching, baselining, and other practices. And of course, the most important is to adopt best practices, which is easy to say, but sometimes it's not that easy to do or to find those best practices. So this is exactly what we're going to talk today. And all those questions and problems that we discuss, they usually open discussions of how to structure the model, what views to build in the model, which artifacts to deliver, in what sequence. This here we're talking about some method. And what I can see that every company deals with the same issue differently. Some use defense architecture frameworks like Department of Defense architecture framework, NATO architecture framework, or Ministry of Defense architecture framework. They all are used in some areas, especially in defense, but sometimes they are considered to be heavyweight, and people just looking for some other options of how to answer all those questions. And there are some MBSE methods as well, like object-oriented system engineering method, Harmony method by IBM, SysMod, FAST methods, and these methods are sometimes used. However, some of them, like object-oriented system engineering method, is very abstract, and when you come to the point where you need to use modeling tool to build your system, you usually run into same questions, and you do not know how to start and how to proceed. But actually, what I want to say that usually in every case you end up with a framework. So even saying there is no framework for it just doesn't work. You always end up using the framework, whether it is a standard-based approach or the approach that you defined. Right? It is just very important is to communicate the framework to the people who are working in the team. So what we are going to talk more today is MagicGrid approach. This is the name for the method that we usually propose or use in our learning teaching sessions and consultancies. So this approach, first of all, presents the grid, which is combined of columns and rows. And the columns, you can see 4 major pillars of SysML, like requirements, behavior, structure, and parameters. And rows here are layers of abstraction. So here we can see concepts, we can see problem, and we can see solution. Sometimes people, they just define concept and problem. Sometimes they just define solution. This is sometimes describes cooperation between 2 different companies, where one company is contracting and the other is contractor. Right? So one prepares requirements, the other builds up solution. So the separation is very important. We are going to talk about that more in details. And so in the intersection of the column and row, you can see the cell. So it explains what kind of information we have to capture here. So for example, if we go to S1 cell, we see that there are stakeholder needs, and we can see use cases, system context, and so on. So we are going to talk about every single cell that we see here. So this is just the organization that helps you understand where you actually are and what models you have to build in one or the other cell, and what diagrams you have to use, which is sometimes very important. And as you can probably see, and maybe you know from practice, that in SysML, most of the diagrams, they are reused for many different purposes. So it's not that you actually know which diagram you use for which single purpose, but you use it for multiple different purposes. And the case study we are going to follow, it is a hybrid vehicle system, and we are going to see the model starting from the concept, then problem domain, and then a little bit of solution models. So we start from stakeholder needs, and we'll switch to the modeling tool, then I switch back to the framework, just to make sure where we are at the present point. So let me switch to the model, and this is the example of our hybrid vehicle. So here we can see our framework, and let me start from stakeholder needs definition. So I just quickly go into stakeholder needs table. So when we talk about stakeholder needs, here we are talking about all the raw information that is coming to the project, whether it's from users or whether it is from business units in your organization, or it comes from some government regulations. This all information in general we call stakeholder needs, and this information sometimes is captured in other tools outside of modeling tools, for example, in some requirement tools, or even in Microsoft Word, Microsoft Excel, and so on. And later you want to have this information to be able to refine these requirements and to be able to trace your system requirements that you are creating further on to the user needs, to have rationale why these system requirements are here. Why do you need system requirements, right? So this gives rationale to have user needs. Example, we can take one of them like quick charge and user. It's very raw text, right? I want to charge vehicle in 30 minutes and drive at least 90 kilometers. So it's very raw information. Then you take this information and make it more formal in the text, or whether at the later stages you can formalize it, and for example, using constraint blocks for the automatic requirements verification. So this is the first cell. Let me switch back to the slides. Here are some definitions. So actually these slides will be shared after presentation. This is also an important point. So the text is added here just for that purpose, that you can read it later on. Once we have stakeholder needs, we want to refine these stakeholder needs, and we are refining these stakeholder needs using use case method. Not all of the stakeholder needs needs to be refined by use cases. Usually we just take functional needs, and for these functional needs we create corresponding use cases. So let me switch back to the tool and go to use cases. So here we are talking about behavior at the concept level, and we are defining what are the users and what are the main use cases, and actually what user wants to achieve with the system that we are producing. And so what you can see in example, we have actor, and this actor is performing several use cases like a drive vehicle or park. There are some more details, like if you want to drive vehicle, of course you have to make sure it's started, and then all you need to do is to accelerate, steer brakes. So these are the main use cases. For every use case, it is a common practice to create an activity diagram and to define flow of events, what's actually happening inside the use case. So if we go, for example, and double click on the braking use case, we can see the top level diagram, activity diagram, where you see what is driver doing and what is hybrid vehicle responding or doing based to the driver actions. So here we have a lot of information already. We have actor used as a swim lane, and we have our system used in another swim lane. So this is context level activity diagram for the particular use case, where we simply define in very easily readable way for the user and understandable way for the user what's happening, right? So these are the main functions of our vehicle for this use case, like brake with generator or engage friction brake. We can drill down further on, and then we would go more into problem definition. So we are actually opening the black box. When we are in the context definition, we are talking about the system as the black box. So we just care about environment, about the main users that are using the system. But once we are drilled down into the definition of the problem, then we are opening the black box, and we are talking about the system, what's happening inside the system, right? So we are going to get back to this a little later. So then after we define use cases, the next step is to go and define system context. Usually in the use cases, we are talking about behavior, and we are talking about actors who are trying to achieve something with the system. So they are trying to perform one or the other behavior, or to invoke one or the other behavior within the system. However, we have a lot more influencers on our system that are actually not performing any functions, but they are very important to capture. Like when we're talking about car, we have in mind weather conditions, we have in mind road, we have in mind these days different kind of communication systems like GPS or GSM, and so we need to define system context. So let's go and see the example of system context diagram. Right, so we just run back. And we go to the system context. And so system context in terms of SysML, it is internal block diagram, so-called IBD. And here we go into one of the contexts that we define. Actually, it is also important to say that we can have multiple contexts. And for us now, it is important vehicle and driving. So the surrounding environment is different throughout different contexts. For example, if you are a maintenance regime, so your model got broken and you get to the service for repair, so then you are in different contexts, and different actors and different relationships are in different contexts. When we talk about vehicle and driving, we have our vehicle as the system. Let me enlarge the diagram a little bit. And we can see all the elements, surrounding elements that are related to our system, like driver, passengers, baggage. We can see GSM, GPS, satellites, and we see environment where we have road, weather, other vehicles around. And we can see the information, very high level information, which is used to communicate between driver and hybrid vehicle, or between other vehicles and hybrid vehicle. We start identifying some of the signals that we are going to use further on. We start identifying, first of all, interfaces. So every connector here, it actually says that you have to have interface when you go to the problem definition at this point. And so this diagram is sometimes used also to depict high-level information, to show it for stakeholders, to present what you're actually trying to achieve. So it usually some nice pictures are used to make it look nicer. The next step, once we're done with this, we go for defining our measurements of effectiveness. So these are the main measurable characteristics, measurable goals that we need to achieve on the system. So we do it in the class diagram, or in the block definition diagram if we are talking about SysML. Let me switch to the diagram. It's actually very simple. So this is where we create value properties for the block, for our main system that we created in the context diagram, which is hybrid vehicle. And here we define main measurements of effectiveness, like stopping distance, battery life, battery charging time. We add additional marking where we say that it is measurement of effectiveness, which comes from SysML specification. So we define all measurement of effectiveness, and then we inherit our hybrid vehicle from our measurement of effectiveness block. We do this just to make these concepts reusable, and once we come to the solution level and we define our system, so we can inherit again and just take the same measurement of effectiveness that we are defining at the concept level. Once we define them, we are moving forward, and then again we are getting back to the use cases. So usually we start problem definition from functional analysis. So we are detailing our functions that we started defining in use case approach. Then we are going further, detailing it in more details. So let me go back to the use case diagrams and go more into details here. Right, so drive vehicle, brake, and here we can go into, for example, brake with generator. So once we go here, we can see that we have swim lanes, and the swim lanes here are the logical subsystems. So we are start identifying the logical subsystems in our system that are responsible for the particular behavior in the system, for a particular function. So this way we are grouping functions. Sometimes these logical blocks are called functional blocks as well, because here we are talking about the behavior, about the functions, and we want to group them. So we create this diagram to explain what's happening, to understand the behavior of the system. Right? Well, if we go back, we can go to the other one, engage friction brake. And as you can see, we have another one where we also have two logical subsystems identified, and we have the flow defined. Right? And this way we can go into more details. And once we want to see our functional breakdown, we can go to the very top activity, which is break, and we can build the structural breakdown just in few clicks, right? So there is activity decomposition map. Once we want to see what we modeled, what the structure, the functional decomposition is, we can build the graph, dynamic graph, and we can see that we have break, inside we have some other functions and so on. And we can just double click to see how these functions are related to navigate to the diagram. So this is a very useful tool to see your functional breakdown. Okay, so once we finish with the functional analysis, we can actually go in more details here. The question is again about granularity, how deep we need to go. This question is the commonly asked question. Usually the answer is that hierarchies like requirement hierarchy, functions hierarchy, and structural hierarchy, they have to have the same number of levels. Once I'm talking about requirements and I'm talking about stakeholder needs or goals and objectives, I have several levels of requirements. Then when I talk about functions, then I have several levels of functions. And I do trace back from functions to requirements at the same level of hierarchy. When I start talking about the structure, which is going to be the next step that we are going to discuss about, then again, I follow the same pattern, right? So I do look into swim lanes, and then I have to make sure that at the first level in my hierarchy, I'm just using the swim lane from the same level of my logical subsystems communication, which is next, right? So then we go to logical subsystems communication, and let's see the diagram that we are having here. So first, it is recommended here to do block definition diagram. According to the best practice is to take your vehicle as a system and identify interfaces. So I mean to create interfaces based on the concept definition that we had. Right? So we are creating proxy ports. We are typing these proxy ports by interface blocks according to SysML. And we want to show these interface blocks here as well, because this is the place where we usually create them. And if you want to make sure that readers can understand this, this is good practice to show some relationship, like for example, allocation to the port. So then all the readers of the diagram, they can understand that this interface block is actually related to this proxy port. Then when we go one level down, or we open the black box of the hybrid vehicle, we go to the internal diagram, and here we show the subsystems and how they communicate. This is a very simplified example of the diagram. But so these are the subsystems that we identified doing functional analysis. And here we are reusing them and showing how they communicate together. What are the structural relationships? What are connectors and what are the interfaces? Once we do this diagram, it is also good practice to take every single subsystem and to do block definition diagram, as well as we did for hybrid vehicle, and to define interfaces, to say what are the interfaces, what are the inputs, what are the outputs, and to also show interface blocks and allocations. So once we get back, there is also good practice to analyze your interfaces if you go into specification of the block. And then you go to ports and interfaces, where you can see your interface control document, what are the interfaces, what are the actually features or the information that they are able to send or they're able to get. And of course the direction and some other details, if they need, they can be accessed here. So this shows the information on the interfaces of the particular system that we are talking about. Okay, so let's go back to the grid again. Let's switch back and let's go to the next step, is defining measurements of effectiveness for logical subsystems. Right, so this is the next step. Fortunately, here I have no example at the present point in this our case study, but usually this is the same as we just looked at the hybrid vehicle level. It is just that we can define some measurement of effectiveness for our logical subsystems. If we have some specific needs, like for example budget for the engine, which is your measurement of effectiveness as well that you have to achieve, or you have you want to define some mass, which is usually more defined like in solution level, but sometimes some of the measurement of effectiveness can also be defined at the logical level. And sometimes it is also common practice to do parametric diagrams here, but we go to the parametric diagrams once we go to the solution level. However, I just want to tell you that it's not only the solution level where we use parametric diagrams. If you see the use for them at the problem level, you can also do that. And finally, of course, goals and objectives. I just mentioned them last, but usually in the normal process, this is constant updating. You keep adding your goals and objectives based on your stakeholder needs, based on the requirements that you get from the user, of course on all the refinement that you did on your use cases, on your system context definition. So this information in P1 cell, it's constantly updated. So it's not that you do it last. You usually start it first, and then you step by step fill it up. Right, so let's go into example and see. We have requirements diagram here, particularly for this, and here we first define our high-level goals, like for example mission statements. So mission statement here can be just build a vehicle that combine an internal combustion engine and one or more electrical motors to move vehicles. And of course then we start deriving objectives, and we can go even in more details, but have to have in mind that here we are not talking about system requirements yet. Right? So first we want to identify what are our objectives. We are still at the problem definition level, which means we are still working on requirements. All the models that we create here, not only in the row of requirements, but also behavioral models, structural models, they are here to refine requirements and to define problem. And the models that we're going to talk about further, they are just to provide solutions, and to make sure that the solutions that you provide, they actually correspond to the problem definition that you have. So this is exactly the next step, solution level. And in this grid that you see here, it is solution level in more details, right? So here, as you can see on the row level, we have on the rows, we have systems, subsystem, and component. In the previous grid, higher level grid, where we display problem and solutions, so here it was just components as the general definition. But once we come to the component level, first we talk about system, then we talk about subsystems, and then we talk about components, and if necessary we go down, dependent of how many levels we need. So we can be very specific on the solution. We can go in very deep details if we need to, if we have to, right? And here it's very important to understand that project governance and project structure is very important. So what we can see in this diagram, so on the left side we can see projects in terms of Cameo Systems Modeler, and on the right side we see our system structure. So first model that you can see, first project that you can see here is the concept and problem level project. So this is where we define concept, where we define problem. We have people working on this. We definitely do not want that our concept definition, our requirements definition would be changed by people taking care of solutions. Right? So they are just using it, but they are not editing this model. That's the common practice. Then once we go to the solution, first we have integration project, which is the system level project. And in the system level project, we are defining our system requirements, our system main behavior, our system analysis models like parametrics that goes on the parametric column. And then once we identify subsystems like brake subsystem on the right, or the cruise control subsystem, the common practice is to create separate models for those, because usually different teams are responsible. Different people are working on these. So they have to work in their own environment for more effective work, and they have to make sure that they are not modifying the system level. which more cares for system engineer, for lead of the system engineering and so on, dependent on the organization. So we have models for every subsystem and for every component. For every component, we need even drill down more, right? And create project for everyone. So this brings you flexibility in managing complex models. It's not that you have everything at the same model, but if you have different teams working, you have to make sure that the configuration management is set up, and you can get the best performance available. And it is also important to note that all the projects that you have here, they all have to have traces to your concept and problem definition. So here it is kind of rationale. So you have to say why you have this component here, where is it coming from, whether it's because of the user need, whether it's because of some functions identified, and so on. So these traces are very important. And here we perform trade-offs. So the general idea is that once you define concept and problem, then you have to find the best solution. And here you are trying to find the best solution, usually from several alternatives. When you go down to the subsystem level, it's the same. When you go down to the component level, it's the same. You do trade-offs. You do trade-offs, and then it is, of course, a lot more powerful when you have separate projects. And once you decide which alternatives is the best, you just pick that project as the one to proceed and add more details, start testing, start simulations, and so on. So once we go to the solution level, we go to component assembly first. This is where we usually start. Let's switch to the project. So now first I show you integration project. So this project is where we have our solution defined. So this hybrid vehicle here is the system that we are providing as the solution. It has trace to the system that we defined in the problem definition, because as you can see in the containment tree, I'm using all the projects from the concept project, logical model that I created before, so I can trace back to them. I also inherit from this same measurement of effectiveness to make sure that this project, this system definition of my hybrid vehicle, it also has all these measurement of effectiveness. And here are defined the main subsystems. So these subsystems here are now already in defined in other projects. And let me switch to some other projects. So for example, there is brake analysis project, which cares only about braking system. So this is about braking subsystem of our vehicle. And as we can see here, we are talking about the wheel, about the brake. So we can see the structure starting from the wheel. The higher level structure, it's in the project, in the integration project. So here we can see only what we care about when we talk about braking. And here, of course, it's very important to trace back. In this example, it's fairly simple. And here you can see again our logical subsystems that we identified, for example, braking subsystem. And we can see our subsystems used in solution level. And we can trace back. So we say that for braking, we need brake, we need caliper, we need pad, we need rotor. So we are more in the physical domain here, right? We need tire, we need wheel, all the things we need. Then, of course, in this level, we build parametrics. So just let me switch one cell more, right? So physical characteristics. So here we want to perform some analysis. In this example, we are performing stopping distance analysis. This was presented in one of the webinars that we had this semester, so you can actually go on our website and find more information. I'm not going to go today into more detail how this parametric works and so on. This is off topic, but this is just to understand what diagrams we are creating here. So as an example, there is parametric diagram that is created to calculate some physical characteristics. Most of the analysis is performed in the integration project at your system level, because this is the level where you want to see how different subsystems communicate together to perform some simulation and some analysis on the integration level. But of course, if you want to perform some tests on the subsystem level, you are doing this in the subsystem level model. Then we go to the component behavior. Let me switch to one other project that I have. So this is for other subsystem, for cruise control. And for cruise control, we have some behaviors defined. So here we are talking about detailed behavior of the subsystem. For example, state machine, which is commonly created at this level. So we have state machine, we can combine them with activities, and actually this project is executable and it's available and distributed with the tools, so you can also try it out. And I'm not going to show you how simulation works here, but I want to show you just that you can go down and here you can create activity diagram. And so this activity diagram is detailed, as you can see. It's a solution level diagram, which is used to have to be able to simulate project. So usually at the problem domain, of course, you sometimes want to simulate. That could also be the case, but in most of the cases, you just build model to understand the problem. Once you come to the solution level, you build a model to be able to answer some questions on physical characteristics, some questions on requirement verification, some questions of how systems communicate or how several subsystems communicate together. So it is more detailed project that you have. And then finally, we come to the requirements, and of course here we have system requirements, we have subsystem requirements, and we have, let me go back to break analysis. So here we have some subsystem requirements, for example, defined, and here we are talking only about breaking subsystem, right? So we have requirements, very clear, very good written requirements. For example, the pod width shall be between 1.5 and 2.5 inches. Right? That's very clear requirement that you can formalize with the constraint block, and then you can automatically verify. So it's no longer some user level raw requirement that comes from the stakeholders. Okay, so this is the grid, but one more important part when we talk about this grid is of course traceability, and traceability here is everywhere between all the cells that we can see in the model. So we can quickly run through some of them, like for example, when we talk about requirements and different levels of requirements, we use derivation, we use derive. When we talk about requirements and we talk about use cases or the functional analysis, we do refine. When we talk about behavior and like use cases and structure, so here we relate based on the subject property of the use case, we relate the use case with the system. Then we have ownership. When we talk about value properties, we have composition. Once we drill down in our functional architecture, we have composition once we drill down in our logical subsystems. We have refine again here. We have allocate when we talk about structure and when we talk about behavior. So we allocate functions to structural components, and we use the activity diagrams and swim lanes for that. We have again here a containment where we own measurements. Here again we have derived. Here we have allocation. So we say that our behavior at the solution level is allocated to the functions that I defined. The same with structure. So I have blocks at the solution level allocated to my logical subsystems. And I have satisfy relationships here. So my functions, they are satisfying system requirements. Again, between behavior and structure, we have allocate. And then again, we own value properties here by the blocks that we have here. So this is more or less the grid. Once we have the grid, we have to define model usage. And this is not yet on the grid. So the grid is more how to create the model, as I explained before. But once you have the model, then you of course are using it. Like you're doing model reviews, you do document generation, you do impact analysis, coverage analysis, automated requirements verification, trade-off analysis, behavior simulations, testing, executable user interfaces, code generation. So these are examples of model usage. Some of them we already covered in our webinar series. Some of them they are coming next year once we continue with the webinar series. And the same with the governance. So also when we talk about governance, we are talking about collaborative environment, about baselining, branching, merging, versioning of the models. Some of the aspects we covered a little bit about how to manage projects and how to relate different projects together, but there are a lot more to talk about. So model comparison, change management, model partitioning, reuse, user permissions, these are all parts of model governance. And again, I'm just referring back to the culture that we define. So we create model, then we define how we use the model, and then it is important how we govern the model once we have it. And so that's it for today from my side, and thank you being with us, and now we answer some.
Thank you, Revius. Let's switch to the question answer session. And give me a moment, please.
Okay, so we have some questions here.
Yeah, I think this one it's really interesting question. You don't mention the use of templates. Do you include modeling templates in your definition for structure?
So actually we are thinking about that. Currently this is, I would say, very new approach. We just started introducing this approach like two months ago. So there are some customers already that are trained on this approach. And we are now just trying to build up more material on this, like record webinar, for example. That was one of the things. Then we are going to provide tutorial and of course some templates in the tool.
A user asks if it's possible to get the sample model being shown by the speaker. If so, how? I would also like the permission to use it in the graduate school lectures in Georgia Tech. Well, I think Aurelius can answer that.
Yes, definitely. We will make this project available. There are still some small things that we need to add, but we will distribute it with the tool in a very near future. And of course, also there will be some tutorials around this model that you can use, and of course, definitely you can use in school for lectures, of course.
We still have some time and some questions. Yes, one cannot define use cases before defining the system context without running the risk to create confusion. Use cases are the direct mapping of the functional interactions between context and the system under design. I think that the order of model creation actions in your grid have to be seriously revised.
Okay, so that's actually a good question, and there can be multiple different opinions on that. Basically, what we have here is coming from the practice in different organizations that we are dealing with, the largest organizations in the world in engineering, and so far we see this like a best way to proceed. Of course, we are always listen to others, and if you have some advices what could be improved, we can definitely consider that and maybe change the grid in the future. So we are very open to that. It's not 100% strict what you have to use. This is just generic basic ideas of how to create your model. step by step, and it's very related again with the modeling environment and the modeling tool, because the modeling tool is one of the three main components that you have to deal with when you do modeling. You cannot do on a sheet of paper, so you have to adhere to the functionality of the modeling tool as well.
Here's another question. Are the slides available? This is a lot of material to digest. Thanks.
Slides will be available. Once we publish the recording of the webinar, we will also share slides.
We received a lot of questions regarding will the webinar will be recorded? Will we get sample? Will we get slides? Usually the answer is yes. We try to publish all the material after the webinar when we summarize it all. I think there's one more question. Yes. Do you have any examples of using SysML for modeling security policies such as allow subject to read object if subject is member of group and time of the day is 8 a.m., 5 p.m., male, female?
Okay, so talking about security and modeling securities, currently we are doing some work on this, so it's not yet available. So we're trying to figure out what are the best ways currently and the standards that we can adhere to provide solution here. But also, if we come to the defense frameworks and once we come to the use of, for example, UPDM as the modeling language, these concepts are captured there. So if you are working in defense domain or you are interested in seeing what are here on the Department of Defense architecture framework side and the UPDM language, so definitely there are some things, but this probably would go as the different discussion. So you can feel free to write us email and we can just provide you with some more information on that topic.
That's a good question. Is a UML background needed? Why are there columns used?
UML background is not needed actually. This is specifically designed for SysML. Of course, you can use it for UML as well, but this is specifically designed for SysML. And most of the concepts that are used here, they can be found in SysML, but of course, as you know, SysML it's just an extension of UML, and just 20% of SysML is complete SysML is actually the extension. The 80% of this is still pure UML. But so it's this difficult question to answer, but basically once you learn SysML, you actually learn a lot of UMLs. Even you do not think that you are using pure UML, you're using a lot that's coming from UML.
And maybe we have a minute for one last question. We got a lot of questions today and all of them will be answered as we mentioned before in written form, but still. The user is asking if the newest UPDM will include security viewpoints.
Yes, it is. The latest version is including security viewpoints and some concepts that can be used for security modeling. And the new UPDM will be completely based on SysML. So actually, you can find it interesting for like security modeling.
Yeah, thank you, Aurelius. Thanks again. And if there's anything that you'd still like to ask, please don't hesitate to contact us with your questions. We appreciate them, and it helps to improve our webinars. Thank you again for your participation, and we hope to meet you again in the upcoming webinars. We wish you very happy holidays.